This is a review for our second exam. This second exam will cover two variable statistics, and first go over some of the formulas that we're working with in this section. The slope, mathematicians usually use the letter M for the slope. Our calculator uses the letter A for the slope. Some statisticians use the letter B1 for the slope. But it doesn't matter so much what letter you use. It's going to be the well, if you have 2 points, x1, y1, x2, y2, the slope of the line through those 2 points is given by the formula y2 minus y1 over x2 minus x1. And then the point slope form of the equation of the line through those 2 points is y minus y1 is equal to m times the quantity x minus x1. And you could use, you don't have to use x1 and y1 here, you could use x2 and y2. There's more than one point slope form. You'll get, if you use x2 and y2, you'll get a different equation, but it'll be equivalent. It'll be the same line, an equivalent equation. Slope-intercept form, there's basically only one slope-intercept form. I mean, you could write the slope first or the intercept first, but essentially they're the same equation. Y equal mx plus b. The m is going to be the same. It could be a fraction or a decimal, but whatever it is, it'll be. It can be expressed differently, but it's basically any equation with that slope and that intercept is going to have to be the same equation. That's the slope-intercept form. So y equal mx plus b, or you could write it y equal b plus mx. Oftentimes, usually mathematicians, at least in algebra courses, will put the slope first, but you could also put the intercept first. And statisticians tend to put the intercept first, y equal b plus mx. Or if you're using letter A for the slope, it's y equal ax plus b. Scatter plot is a two-variable graph that shows the relationship between two variables. So these first few formulas apply to a line through 2 points. For the two-variable graph, the scatter plot, you'll have a lot of points that are not necessarily on a single line. So scatter plot, you might have a graph that looks something like this, and the dots oftentimes will be close to a straight line but not exactly on the straight line. So what we want to do is find the best line that fits this data. So we want a line that sort of comes close to at least most of the points in this data set. So we're using a two-variable graph to sort of visually tell us the relationship between the two variables, x and y. Could be length of pregnancy and birth weight, or whatever the two variables are, the weight of the car and the miles per gallon. And then there's a statistic that tells us more precisely what the relationship is between the two variables. This is a sort of a complicated formula here, but if you break it down, it's not so bad. When you're doing the operations, you want to first do what's inside parentheses. And if we look at what's inside parentheses, you may recognize that what's inside parentheses here are z-scores. Z-score is the score minus the mean divided by standard deviation. So we have the z-score for x, compute that for each value of the variable, and then the z-score for y, multiply the two z-scores together, then add them up and divide by n minus 1. And it's quite a bit of computation, but it sort of does sort of help if you think about the formula in stages here. Once you have R, then that's the hardest part of the computation. The slope then is r times the standard deviation for y divided by the standard deviation for x, and that's the best fitting slope, the slope of the best fitting line for that data set, and the intercept of the best fitting line for that data set is the mean for y minus the best slope times the mean for x. There's some regression theorems. I'm not going to emphasize these too much, but they do show up at some of the exercises. What they're calling SSE, I like to call it the sum of the squared residuals. They call it the sum of squared errors. I'll go over that in a little bit, but the total sum of squared differences, like y minus y bar. This is if you divide by n minus 1, you get the variance. So you recognize this is kind of related to the variance. Basically, the variance for the y variable can be broken down into two pieces. One has to would be one piece is the sum of the squared errors, or the sum of squared residuals, and the other piece is the predicted value minus the mean and squared that. So anyway, the total sum of squares can be broken down into two pieces, and r squared, that's correlation quotient squared. Another way of computing that is this SSR here, this sum of squares here divided by the total sum of squares. Okay, so let's get into some specific examples. I'm going to start out. The first formulas I had here were for lines through 2 points, and so I'm going to start out with that. We're given 2 points here. If you have more than 2 points and not all on the straight line, then that's a little bit different. Then we'll get into that formula in a bit. But I'll start out with an equation of lines through 2 points. So we're given 2 points here. We have the point 1 comma 1.5 and the point 4 comma 3. And I can label these, I'll label these x1, y1, and this one I'll label x2, y2. So then the slope is going to be the difference of the y values divided by the difference of the x values. Some people call it the rise over the run. See if I can have a pen here. So this piece here would be the run, and this piece here is the rise. So it can be expressed as terms of the rise over the run. But anyway, the difference of the y value. So it's y2 minus y1. So it's 3 minus 1.5 divided by 4 minus 1. Okay, so it's going to be 1.5 divided by 3, and that comes out to be 0.5. So our slope is 0.5. You could also write it as a fraction 1/2. And then the slope-intercept form, you plug into this formula here, y minus y1 equals m, x minus x1. Y1 is 1.5, and it doesn't matter. You could use x2 and y2 in this formula. It'll give you a different equation, but it'll be an equation for the same line. M we just computed, 0.5. X minus x1, x1 is 1. Okay, so that's the point slope form. Okay, these instructions I have to reverse. This is the point slope form. And we want the slope-intercept form. It's called the point slope form because you're given a point. Looking at the equation, you see the point 1.5, and you see the slope 0.5. Okay, So if we simplify this, we can get the slope-intercept form. So if we distribute the 0.5, we'll get y minus 1.5 equals 0.5x minus 0.5. And then we want to solve for y. So we want to add 1.5 to both sides of the equal sign. And that'll give us y. These will cancel. Minus 1.5 plus 1.5 cancels. And this is 0.5x or 0.5x minus 1. Negative 0.5 plus 1.5 is 1. So that's the slope-intercept form. So there can be more than one point slope form, but there's basically only one slope-intercept form. And this gives us the this is plus 1. Negative 0.5 plus 1 is plus 1. This tells us that the y-intercept is 1, this equation. This is the y-intercept, this is b. You can also estimate the y-intercept from the graph. The y-intercept is where the line crosses the y-axis. So it crosses at about 1. So you can sort of estimate it from the graph. But this form tells us exactly what the y-intercept is. Okay, so here's another example. Now here we have more than 2 points, and so there's not necessarily one straight line that's going to go through all 5 of these points. We have the data from 5 students on hours spent watching TV and hours spent doing homework. So we want to use the formulas that I just mentioned. These first formulas, the slope and the point slope form, the slope intercept form. You can use those if you have 2 points and you want the line through those 2 points. But if you have more than 2 points and they're not necessarily all in a straight line, then we want to compute the correlation. But before you compute the correlation, if you look inside the formula for the correlation, what we need to compute that is the mean and standard deviation of each variable. We need the mean and standard deviation of the x variable, mean and standard deviation of the y variable. So for this data set, we're going to start out computing the mean and standard deviation of the TV hours. If we add these up, the x values up, we get 15. Divide by the number of students. There's 5 students. We have a mean of 3. And then to compute the variance, each score minus the mean, square it, add those up. 1 minus 3 is negative 2. Negative 2 squared is 4, and so forth. Negative 2 minus 3 is negative 1. Negative 1 squared is 1. When you're squaring the minus sign, you need to square the minus sign too, not just the number, but the minus sign. So negative times a negative is positive. So this last column is all positive. These add up to a total of 10. Divide by 4, you get 2.5. And then if you take the square root, you get a 1.58 something. And then we want to do the same thing for the y variable. So I left off some of the steps here, so I'm going to the mean for, so here's the y numbers. The y variable is the amount of time, number of hours spent doing homework. These add up to 10. So the mean for y, 10 divided by 5 is 2. And then, so in this column here, we want each score minus the mean. So it's 5 minus 2 squared. That's 3 squared, which is 9. 3 minus 2 squared. 3 minus 2 is 1. 1 squared. 1 times 1 is 1. 2 minus 2 squared. 2 minus 2 is 0. 0 squared is 0. 0 minus 2 squared. Negative 2 squared. And we're squaring the minus sign. Negative 2 times negative 2 is 4. And this is going to be 0 minus 2 squared again. Negative 2 squared is 4. So if you add these up, we get a total of 18. And so the variance, n is 5 students. 5 minus 1 is 4. So variance is 18 divided by 4, which is 4.5. And if we find the standard deviation, we get 2.12 something. Okay, so now we've done sort of the preliminary steps in computing the correlation. We have the mean and the standard deviation of each variable. And so now we need to compute all the z-scores. So the z-score for Anna, and I'll get another piece of paper here. So for Anna, the xz score, we have x minus x bar over sx. That's going to be Anna's x value is 1. So that's going to be 1 minus the mean for x is 3. Standard deviation, this is the 1.58 something. Back to 1.58. It'll help if you put these, store these in memory in your calculator, so you don't have to keep typing them in. Put this in a calculator. Okay, so second square root, 2.5. Okay. Okay, so okay, so I get 1.26 something. Negative 1.26 4911.064. And then the z-score for the homework hours, y minus y bar over sy. Now Anna spent 5 hours doing homework, 5 minus 2, the mean homework is 2. And the standard deviation 2.121320344. And that comes out to be, let's see, what is that? Let's see, okay, so this 3 divided by second recall. Oops. .41 something, and that's will be positive. Okay, so we can put those numbers into this chart here. For Anna, it's negative 1.26 491.064, and this one was 1.41 42 3562, and if we multiply those together, we'll get negative 1.78 something. 88,54382. Okay, and then we can do the same thing for Ben. Next line is Ben. X minus x bar over sx. So Ben had a 2, homework score was 2. I mean, the TV score was 2. 2 minus 3 divided by 1.58 something. And I think that comes out to be, that's going to be negative also, negative 0.632. 4.55532. Okay, and then the other one, Ben's z-score for homework. Ben spent 3 hours doing homework, so it's 3 minus 2, 2.12, and that comes out to be negative, no, positive 0.47. Okay, so we can fill those numbers in. So this is going to be negative 0.632, 45532, and this one is going to be negative positive 0.4714044521, and multiply them. Negative times positive is negative. You get 0.298, 142397. Okay, so I already filled in for the other 3 students, and the column we want is this last column here. These 2 columns should add up to 0. You could use those as a check, but the column that we're actually use for the next step is this last column here, and we want to divide that by n minus 1. So in the formula for the correlation coefficient, after you add up the products of the z-scores, the last step is divide by n minus 1. So there's 5 students, 5 minus 1 is 4, divide by 4, that gives us the correlation coefficient. So this is close to negative 1. The correlation coefficient is always between negative 1 and 1. It was close to negative 1, it indicates a strong negative correlation. So that means they're close, the points are close to a straight line with negative slope. If it's close to positive 1, that would be close to a straight line with positive slope. So anyway, this is strong negative correlation. As the TV hours go up, the homework hours go down. There's also, I mentioned before, that R squared is called the proportion of variability. If you square that, you're squaring the minus sign also, so negative times negative is positive. You end up with 0.938 something, or approximately 0.94. And that gives you the percent of the variance of the y variable that's explained by the x variable. So in this case, 94% of the variance of homework hours can be explained by TV hours. Okay, so then we can go on to let's see, next here we can compute the slope of the best fitting line. So again, we're past the hardest part of the computation. Once we get R, then the rest of the computation is not so bad. So R is negative 0.96896. 96896296279, and the standard deviation for y we computed before was 2.12, 132, 0.344, and we want to divide by the standard deviation for x, which is 1.58. 113,883, and that comes out to be negative 1.3 homework hours per TV hour. So it's always y variable per x variable, the unit of measure. And then once we have the best slope, or the slope of the best fitting line, we can compute the y-intercept, and that's with this formula here, y bar minus a times x bar, and mean for y is 2, the mean for x is 3. We have a double negative here because the slope itself is negative, so that becomes a positive. 2 plus 1.3 times 3 comes out to be 5.9 homework hours. And then we can write down the equation. So the equation is of the form y equal mx plus b, or y, you can write it y equal ax plus b. So the x variable is TV, the y variable is homework, slope is negative 1.3, the best intercept is 5.9. We can also, now this is a lot of computation, you can check your work on the calculator. You push clear while holding the on button, then clear, then second data, right arrow, enter data, and put in all the data, push that bar, and then you can scroll over to get the mean and standard deviation of each variable, and also A, B, and R. So you can use a calculator to verify your information. But for the test, you should show at least some steps as if you did not have it use a calculator, just so that I know that you know how to use the formulas. You can do part of it on the calculator if you want, or verify your answer on the calculator. Okay, so we can also compute the for each student, we can compute the prediction error. For Anna, Anna spent 1 hour watching TV, so Anna's predicted homework hours would be well, our equation negative 1.1. So our equation is homework equals negative 1.3 times TV plus 5.9. So in Anna's case, Anna's predicted homework hours, so it would be negative 1.3 times 1. Anna spent 1 hour watching TV plus 5.9, and that comes out to be 4.6 hours. So Anna's predicted, based on this equation, Anna's predicted homework hours are 4.6. Anna's actual hours, or the observed hours, is 5. So that the residual, the actual minus the predicted, so it's going to be 5 minus 4.6, which is 0.4 hours. So I can write these in here. The predicted was 4.6. The residual, 5 minus 4.6, is 0.4. Some of these residuals are negative. If the actual is less than predicted, it'll be negative. In this case, as actual was more than predicted, so it's a positive residual. And then we square that. 0.4 squared is 0.16. Okay, so I did that for each of the students. I computed the squared residuals. If we add these up, these add up to 1.1. And there's a theorem that says that the formula that we used for computing the best fitting line has actually the smallest sum of squared residuals. So for this data set, any other line would have a larger sum of squared residuals, or in the book calls it sum of squared errors. A lot of books call it sum of squared residuals. Okay, so let's make a scatter plot. A scatter plot is a graph that sort of visually shows the relationship between the variables, and maybe not as precise as these formulas, but it provides a good residual relationship. So let's put down the information we know here. We have TV homework and the predicted homework. Okay. So we have 1, 2, 3, 4, 5. We have Anna, Ben, Chelsea, Dante, and Ellen. Okay, so and we just we were given the homework hours for each student also, so it's 5, 3, 2, 0, 0, and we just computed the homework. So this hat is often used to mean the predicted Y value. So for Anna, the predicted was 4.6, and for Ben it was 3.3, Chelsea 2, Dante 0.7, and Ellen negative 0.6. So that's the predicted. And so let's make a graph showing both of these. Okay, so we'll have okay, so I'm going to use different colors for, I use red for the actual and green for the predicted. So for Anna, Anna spent 1 hour on TV, 5 hours on homework. So I'll put a red dot there. That was the actual homework. The predicted homework was a little bit less than that for Anna. It was 4.6. Put a green dot there for that. That's the predicted. For Ben, Ben spent 2 hours on TV, and Ben's predicted, our actual homework was 3 hours. So I put a dot here for that. And Ben's predicted was 3.3, so that's a little bit above. I'll put a green dot for that. Chelsea, predicted, Chelsea was 3 hours on TV. The predicted homework was 2 hours, so I'll put a red dot for there. And Chelsea's predicted was also 2. So it's going to be a little hard to put 2 dots in the same spot, but we'll just have to remember that predicted and is the same as the actual for Chelsea. Dante, the actual was 4 hours, and the predicted was 0.7. And Ellen, 5 hours, and the predicted was negative 0.6. So let me go down here. Oh no, I got the wrong color there. I want the green dot here. Okay, so so then I can connect the green dots. The green dots will actually be my prediction line. I'm maybe a little bit off with my graph here, plotting the points, but so that's my prediction line. You can see that well, it's a line. The line goes down as you go from left to right. So that from the graph we can see that the line has a negative slope, and whether you're looking at the red dots or the green dots, it goes down. We see that the green dots and red dots are reasonably close together. Some of the red dots are above the line, and some of them, we have 2 of them are actually above the line, and 3 of them are below the line. So that can be expected. Usually not all the dots will be right on the line. And the difference between the 2 dots is the residual, or the prediction error. This is and this residual was 0.4, right? That's the difference between the predicted value and the actual value. So you can see the graph kind of illustrates the residuals, the prediction errors here. Now the red dots would form the scatter plot. It's called the scatter plot, and the green dots are the prediction line that I did on top of the scatter plot. And that concludes this presentation.